Right. So let me just quickly introduce you to the audience. So Dr. Brian Keating is an experimental physicist at the University of California, San Diego. He is the best-selling author of two books, Losing the Nobel Prize and Into the Impossible. He is also the host of the podcast of the same name, Into the Impossible. So once again, Dr. Keating, welcome to the podcast. It's great to have
Ah,
you.
it's great to be with you. It's a great honor, and it's great to talk to your millions of fans and those that depend on you for great information, of which I am one. Thank you for having me.
Thank you. So we're going to discuss a whole lot of topics: the Big Bang theory, the origin of the universe, possibility of life in the universe, multiverse, and other things. But let's begin with topics related to the research that you're doing. So could you give us a brief history of the universe? The best model of the universe that we have is the Big Bang cosmological model, the lambda CDM model. So could you give the audience an overview of how the universe began? How did it end up the way it is today?
Yeah, so that's actually a very timely question, no pun intended, because people are debating very, very vociferously the origin of the universe and whether or not it was a singular one-time event, whether it was a quantum event, whether it was a classical event that can be understood, and whether or not it was preceded by another universe, or perhaps accompanied by not just one universe, but it's called in the multiverse, perhaps an infinite number, 10 to the 500 or more other parallel universes. And so in some sense, it's an unresolved question. What we do know is going backwards from today. If we take today and we go backwards 13.8 billion years, we will come to a very, very different set of conditions in the physical universe. We would have a very hot, very dense plasma suffused with protons and neutrons, neutrinos, and other subatomic particles. And that epoch is really the end of where we really understand physics based upon laboratory experiments that we can do today. In fact, that my colleagues do at the Large Hadron Collider. They can replicate conditions going back 13.8 billion years with only a slight difference of about a second, or maybe even less than 1 second, from perhaps the origin of time, perhaps the origin of space, perhaps the origin of our universe, but definitely the beginning of what's called our observable universe. And our observable universe are all the things that have had enough time for their existence to reach us via electromagnetic rays, or by the existence of subatomic particles that we can still examine today. That era is called the Big Bang. We don't think of the Big Bang as synonymous, as equivalent to the origin of time as professional cosmologists. We say that the origin of time may not be understandable within the laws of physics, and yet we have a vast amount of very technical, quantitative, detailed understanding of the properties of the universe from that point in time, fractions of a second, going forward. Now, what my research centers on is trying to go back even further. We've gone back in just 90 years from what was thought to be an infinitely old universe, a universe that was thought to exist even by Einstein for all eternity. And we have now understood how the universe has been evolving, not static as Einstein initially thought. And that revolution continues. We're trying to build instruments. I am not a theorist. I do not construct theories of wormholes, of black holes, of other kinds of holes. I don't do any of that. I look to try to prove my friends that make those theories wrong, not right. We're not in the business of proving somebody's theory right. No, we're in the business of proving people's theories wrong. And then what we're left with will be an approximation to how the universe came to have the appearance that it does today. That's the job of the Big Bang cosmologists, of which I am one. And what we found is a universe filled with matter, obviously, filled with radiation of different types, and we hopefully can get into the different types of radiation. That includes neutrinos, photons, gravitational waves, and many other forms of signals from the earliest moments in the universe. We see a universe that's dynamic, that's expanding, that every single object that we can see is moving away from us to very high approximation, except for maybe a dozen or two that are gravitationally attached to the Milky Way galaxy. And we see a universe that's suffused with leftover heat, which is actually quite cold, and that's quite good for us. And I know you've talked about this many times, called the cosmic microwave background radiation. And that type of radiation has suffused the cosmos, has cooled off from thousands of degrees to just a mere 3 degrees above what's called absolute zero. That is very precise physical evidence that has revealed the existence of not only ordinary matter and radiation, but dark matter, dark energy, and the presence of many exotic forms of matter and radiation that we can discuss today. But more importantly, Abhijit, is that it's helped us understand where other alternative cosmologies, infinitely old universe, static universe, et cetera, have changed. And on my channel, I like to pride myself that I talk about alternative models that are precise in their predictions. Right now, there's a lot of controversy going around saying the Big Bang didn't happen and that there are other explanations for all the phenomena, and the Big Bang's in trouble thanks to the James Webb Space Telescope, which I hope we can chat about. And nothing of the sort could be close to the truth. We actually have more confidence in the origin of the universe emerging from a Big Bang, not necessarily a singularity, another universe. We have to discuss that. But we have more confidence in the quantitative, not qualitative, quantitative description of nature than we've ever had. And on my channel, I discuss with other esteemed colleagues the proof or disproof of the standard model and how we can adjust it to better match observations, perhaps by bringing in things like the multiverse, quasi-steady states, things like that, but perhaps not. So that's a description of what I do for a living. I build telescopes. I've been to the Antarctic South Pole twice to build a telescope called BICEP, and with my colleagues. And now with my colleagues in Chile, we're building $100 million cosmic microwave background observatory to look for the imprint of waves of gravity on the waves of light emanating throughout the universe. So that's my daily job.
So let's talk about the CMB, the cosmological microwave background radiation. So the cosmological redshift distance relation and the CMB are two major pieces of evidence that provide very strong support for the Big Bang theory. Now, the new observations from the JWST, the James Webb Telescope, have caused a controversy. So what's this new raging controversy all about? And how do the JWST observations of the earliest galaxies supposedly prove that the Big Bang theory is incorrect?
Yes. So I liken it to the situation in physics and in astronomy in 1968. So in 1968 was before humans landed on the moon. And we were trying to understand the origin of the solar system. In particular, how did the Earth form? How did the moon form? And what were the other origins of the planetary conditions that caused our solar system to look the way it does? In 1968, we had very little physical evidence because we hadn't had astronauts scoop into the moon and bring back pieces of it here to Earth. And so we lacked hard physical evidence. We had a lot of observations. Now, once we went there, then we refined our model of the lunar formation theory, and it's still a theory. We can't prove it. There were no video cameras. There was no live streaming of the event, but we think it was due to a large collision of a very, very large subplanetary body crashed into the Earth, the primordial Earth, and dissociated it, fragmented it. And we see object properties similar to the crust of the Earth in the entirety of the moon. In other words, the moon doesn't have a solid iron core and it doesn't have liquid, surrounding that inner core. And those are things that the Earth has that the moon doesn't have. So it is likely that it didn't form via, capture or the exact same processes that form the Earth. It's probably formed from a collision. Now, is that proof? No, but we have good evidence for it. Now, you wouldn't say that discovery then invalidates Isaac Newton's laws of gravity, which underpin the solar system planetary formation. You wouldn't say, "Oh, well, the moon is too big to have gotten that way," and therefore, not only is your theory of formation of an astrophysical object, namely the moon, not only is that wrong, Abhijit, but it's completely wrong. Your notion of gravity and condensation, and actually, there's some other force, electricity, that's holding the moon. So that's what's happening with this recent controversy. There's a claim that the formation of galaxies with slightly more structure about 1 billion years after the Big Bang has called into question not just the Big Bang itself, but the theory of relativity, the gravitational properties of matter, and a host of other objects. And not only that, according to the main proponent of it, but it is evidence for a theory that's been ruled out literally for 90 years called the tired light hypothesis, which in their model, they assume a static universe. And they're saying in a static universe, obviously, there's an infinite amount of time for galaxies to have their spiral structures that are observed in some of the James Webb Space Telescope data. Now, I've done 2 videos now, including one with my colleague, who's a professor in Sydney named Geraint Lewis, and refutation of this idea. And the primary way to understand it is that the Webb telescope simply cannot look back to an early epoch before galaxies formed, because it is sensitive to infrared light, just as Hubble couldn't look back as far as James Webb can look back, because it was limited its electromagnetic spectrum. And I know you talked about the electromagnetic spectrum about a week ago on a similar show, and so I won't belabor it, but the electromagnetic spectrum is an infinite distribution of photon characteristics. And the Hubble had slight amount of infrared capability, but not much. James Webb is designed to do that, to specifically look for highly redshifted light due to the expansion of the universe, evolving and increasing over time, such that galaxies that are farther away are moving faster away and therefore are more Doppler shifted and therefore are more red. Now, of course, when you have a new technology, you see things you couldn't see with the earlier technology. When Galileo used the telescope for the first time in 1609, he looked up and he saw things that you couldn't see with the naked eye. He didn't go back and say, maybe all the laws of science need to be overthrown because it's simply not possible in my limited comprehension to develop a moon around Jupiter. No, it's impossible. Like, it would take too long. And no, he didn't say that at all. He said, let me investigate the capability of this new instrument. So with James Webb, we have zero evidence for the incompatibility of the Big Bang theory. In fact, it's more evidence than one could have previously even collected using the Hubble telescope. So I think it's almost anti-scientific to say that this now calls into question. The believers in this alternative model suggest the universe is not expanding. They suggest that the universe cannot evolve to form galaxies in such a short amount of time, and they misconstrue what the Big Bang actually says. The Big Bang doesn't say anything about the formation of galaxies. Oh, and as a bonus, Abhijit, they have a theory of the universe that's completely incompatible at what's called 100 standard deviations or more with observations. They have no explanation for the cosmic microwave background radiation. And worst of all, this is a sociological point, which I know you talk about science and society. They are calling into question the intellectual honesty and integrity of my colleagues. Now, I don't work on the Webb telescope. I've interviewed the chief scientist who won the Nobel Prize, John Mather, and many other people involved in it, and including the people that wrote this paper that has been cited as evidence supposedly against the Big Bang. And they accuse me of being blind and ignorant about alternative models because I'm making my money from the Big Bang theory. And I don't even really respond, but I did want to, I posted on my my video, that's the video for people that haven't subscribed to my channel, Dr. Brian Keating. I posted an interview with one of the most renowned cosmologists in history. His name is Jayant Narlikar. And if you haven't met him, Abhijit, you should meet him. He's at Pune. He and his wife, Mangala, are some of the brightest intellects in the world. I actually had the honor of meeting Jayant many times here at UC San Diego. Why? Because the person whose office that I inhabit today, his name is Jeffrey Burbidge, or was. He passed away in 2010. He and his wife, Margaret Burbidge, along with Willie Fowler and Fred Hoyle, who came up with the name Big Bang as an insult because they didn't believe in the Big Bang. Jayant was one of Fred Hoyle's students, his best student at Cambridge. Phenomenal intellect. Jayant still believes in what's called the quasi-steady state universe. And if you have any doubt about my intellectual honesty or my willingness to consider alternatives, watch that video with Jayant. It's pinned on my channel. He is and his wife are delightful, truly intellectually honest, brilliant scientist and mathematician in her case. And I have no problem talking to them. Why? Because they don't cast aspersions on my integrity. They speak in the most quantitative possible terms. They don't have polemics. They are true scholars. And so that was kind of my subtle response to these people saying, don't trust Keating, don't trust his colleagues, don't even trust the Webb telescope. We have the right idea. Oh, and by the way, these people, their main goal is to support fusion research that they're doing privately funded, luckily, that they happen to have the secret to the universe, according to them, and they can reveal it if they get more money. And so if anybody has a financial ulterior motive, it's not me.
So, talking about alternative models to the Big Bang, what would you consider to be the strongest arguments in opposition to the Big Bang? I mean, for instance, there is the one of the examples is that the Big Bang theory depends on the cosmic inflation hypothesis, the theory that at the outset the universe expanded superluminally. So, is there any experimental evidence for inflation? If there is none, then does it mean that that's an argument against the Big Bang? What would you say?
Yeah, so there's a difference that we have to distinguish between cosmology, which is the evolution of the universe, and cosmogony, which is the genesis or cosmogenesis. So imagine you study the theory of evolution and you say, well, we don't have an explanation, which is true. We don't have an explanation for the origin of life, not only on Earth, but in the universe. And actually, Fred Hoyle, Jayant Narlakar's advisor, had some ideas about this as well. We can talk about that some other time. But the idea that you could invalidate Darwin's theory, or you could call it into question the theory of evolution, which depends on genetic evolution and genetic heritability of chromosomes and traits, that you could invalidate Darwin because we don't have an explanation of how life got started on Earth, is not fully intellectually honest, in my opinion. And so it is true that we lack an explanation for the very origin, T equals 0, the moment of time at which everything came into existence. It is also true we lack a theory of what's called quantum gravity, where we don't understand the reconciliation of how the laws of gravity mainly manifest on classical, very large scales, and the laws of the quantum can interact in a self-consistent way. We don't understand. That's true. And in fact, there may be no such theory of everything, TOE. That might not exist. We assume that it may exist. Many of my colleagues have looked for it. Einstein looked for it. We still haven't found it. That's because it may not exist, or it may be at such high energy scales we'll never have access to it. Either way, despite those lacunae, those gaps in our understanding, it does not question the underlying evolution and origin of matter that we observe. That happens long after the moment of time. Remember, and you know this, but physicists don't think of time linearly. We don't say, oh, 1 second after the Big Bang is the same as 300 seconds after the Big Bang is the same as 9,000 seconds. No, we think logarithmically or exponentially. We're trying to go right now from an understanding of the universe, say at 10 to the minus 9 seconds. The time is inversely proportional to temperature of the universe. So at that time, at a time about 1 nanosecond after the origin of our observable universe, that could have been because a previous universe collapsed. It could have been because it came into existence at that time. We are going back another 27 orders of magnitude, potentially, in the experiments that I build. So the experiments that my colleagues and I build are looking not for strange particles, not for new forces. We're looking for known physics, the physics of what's called gravitational radiation, a direct consequence of Einstein's theory of general relativity. He didn't actually believe it. Einstein didn't believe you'd ever detect gravitational waves. He didn't believe you'd ever detect gravitational lensing. Einstein made a lot of blunders, Abhijit. I don't know if I always say it's too bad he could have had a good career. He could have been somebody. But he had about 7 blunders. And I always put that down as a reason that you shouldn't worship men. In other words, we have my second book is called Into the Impossible. It's a collection of 9 of the 13 interviews I've done with Nobel laureates. And in one of those interviews, I interviewed Barry Barish, who was one of the leaders of the LIGO, Laser Interferometric Gravitational Wave Observatory, that detected gravitational waves and announced it in 2016. They won the 2017 Nobel Prize. That he was one of the winners. He told me when he won the Nobel Prize, he had the imposter syndrome. I said, why? Why do you have the imposter syndrome? You won the Nobel Prize. It's the highest honor any human scientist could ever achieve. He said, no, it made it worse. I said, why, Barry? He said, well, when you win a Nobel Prize, you go to Stockholm, Sweden. You're celebrated. You're feted. You're given feast and food, and you meet kings and queens, and you bow, and you wear a tuxedo that costs more than my first 3 cars put together. And when you go there, you have to collect your medal, which is solid gold or gold-plated metal, and you get a check for your share of $1.5 million US dollars. He said, when you get it, they want to prove that you're not going to come back. They trust you, but they don't trust you that much. They want to make sure you're not going to come back and say, where's that check? I got the medal on stage. And they said, you sign a book. Barry told me, you sign a book. And it says, I testify I received my money and my medal. Mm-hmm. He said he's a curious fellow. He looked back. Who did he see? He saw Chandrasekhar. He saw Feynman. He saw Madame Curie. But then he saw Einstein. Mm-hmm. He said, I'm not worthy. I don't deserve to be in a book. I'm just a guy from Oklahoma. I don't deserve to be in the same league as Einstein. I don't feel worthy. I have the imposter syndrome. I said, Barry, guess what? Einstein felt the imposter syndrome. He said, what are you talking about? I said, Einstein felt that Isaac Newton did more for science, math, physics, and society of civilization than any other human being before or since. He said, I'm not worthy of Einstein. Guess what? Newton had the imposter syndrome. He wanted to be like Jesus. I don't know if you know this, but he claimed his greatest accomplishment was that he was celibate his whole life, and that he was like Jesus, and only that way. So we all have these. So never feel like you are not as capable, not as, and I actually think it does a disservice when people have the imposter syndrome, because you say, I'm not like Einstein. I'm not like Shonda. I'm not like whatever. And then you don't do the thing that they weren't always. You think Einstein or Chandra, you think they were like that at age 5? I've got young kids. You have to encourage them. And if you tell them you'll never be like somebody, they'll never be like. Anyway, that's a digression. The point being, Einstein didn't believe in the expanding universe until he was shown physical evidence. That physical evidence was the recessional velocities of a dozen galaxies or so that Edwin Hubble had observed. And that he instantly, in an act of great scientific integrity, changed his mind. And so all these things that we're looking for, including Einstein's prediction of unknowingly the existence of waves of gravity that can be produced if inflation took place, which is what you were inquiring about. If inflation took place, there should be unequivocally a background in space-time, ripples in space-time that are the result, perturbations in the gravitational force field that are produced by gravitons that exist for infinite amounts of time, just like photons do. They don't age. And these gravitons could then make their way through the universe to the age at which the universe was when it produced the cosmic microwave background. If they exist, they will cause the microwave background to inherit a type of property called polarization. Polarization is the effect of when matter interacts, or light interacts with matter. Unpolarized light, say from the sun, bounces off the Pacific Ocean here, and it changes its polarization state and suppresses some of its properties. And we observe that that's why we wear polarized sunglasses when we go to the beach. On the other hand, in the early universe, waves of gravity can polarize the CMB, the cosmic microwave background, and we could possibly detect it. Now, we claimed once before to have detected it with my project, the BICEP team. And that's the subject of my first book, Losing the Nobel Prize. Spoiler alert, we didn't detect it, because if we detected it, we would have won a Nobel Prize, because it would have marked the earliest physically, humanly, theoretically possible moment in which scientists could ever go back in time. It would mark not just a second, not just a billionth of a second, but a billionth of a billionth of a billionth of a billion, 10 to the minus 36 seconds after the Big Bang, a couple of hundred what's called Planck times. And that would be the earliest fossil physical evidence. We're still looking for it. That's the main goal of the Simons Observatory, now is in Chile. That observatory, $100 million project that I co-lead with many of my other fellow colleagues around the world. That project is going to get its so-called first light or first microwave in 2 years. It will have capabilities that the BICEP and BICEP 2 experiment did not have. And our colleagues around the world are also looking for this because it would be the most significant evidence of the Big Bang. But again, would it be time equals zero? No. We have no thoughts on whether or not we could distinguish time equals zero. But what we could do, again, our job is not to prove the people, Alan Guth, Andre Linde, Paul Steinhardt, our job is not to prove them right. It's to prove other theories wrong. And so one of the theories that could be proven wrong is the existence of an earlier universe that collapsed, like a big bounce, a previous universe, maybe an infinite cycle of cyclic universes that come into existence, expand, accelerate, and then the accelerated energy decays through some mechanism we don't understand. That decay leads to a collapse, and then that nucleates a new Big Bang. That could happen once or an infinite number of times. But nevertheless, even if it takes one bounce or an infinite number, no waves of gravity are produced in such a model. Therefore, if we see the imprint of these waves of gravity, primordial waves of gravity, we would rule out a class of models that has been around for over 2,000 years. So it's quite exciting that we can even contemplate to do this, and we will do it. We will have answers in less than 2 years.
That's very exciting. So talking about the BICEP 2 experiment, you did not win the Nobel Prize. You thought that you had a result that would give you the Nobel Prize, but eventually it emerged that there was some space dust or something that caused you to have to retract this. So could you tell the story about that?
Yeah. It is the story of my first book called Losing the Nobel Prize. It's a story of a memoir. It's an autobiography, and it explains what goes into a building of a scientific experiment. I know that you've talked a lot about the great theoreticians, and we've already mentioned many of them, including Stephen Hawking. We've talked about Einstein earlier today. Brian Greene, Lisa Randall, these are wonderful, brilliant scientists. Guess what they all have in common? They're all theorists. They're all theoreticians. I realized there's no book for a young person like me, even though I was influenced by those, and they're my friends, who likes to build things, who likes to work on his car, who likes to do experiments, chemistry, that there was no guidebook on how to learn about doing actual astronomy and building actual telescopes and how they work. All you get is the finished product. There's wormhole and there's Hawking radiate, but how do you actually measure it? How do you actually build an instrument? And I wanted to do that. I want to write the first ever book about that. And some people advised me not even to talk about the Nobel Prize because it may be detracted from the story. So actually, the Nobel Prize is only 3 chapters out of 11, and most of it's about the origin and history of how we came to believe throughout cosmic time that the universe had an origin and what it would mean to make such a detection, both scientifically, but also philosophically, maybe spiritually. I am a religious person. In my case, I'm a Jewish person. And that influences some of my philosophical, but not scientific endeavors. And what I decided to do after many years of thinking, I wanted to do something very significant, was to build a small telescope. It's less than the width of my arms across. And I wanted to build a small refracting telescope, just like my great hero Galileo did back in 1609. And that was to build a refractor to not look at planets, not look at phases of Venus as Galileo did, but look back to the origin of time. Now, we couldn't use ordinary eyes attached to tubes of telescope. We had to build a microwave telescope that could see microwaves, detect them, resolve their polarization, and also resolve their electromagnetic spectrum, what portion of the spectrum that you've talked about many times on this channel. And to do so, we require to build a special kind of detector called a superconducting bolometer. Now, what is a bolometer? It's very simple. If you go outside when it's daytime, I know it's night there, but if you go outside and you close your eyes, you can still, quote unquote, see the sun. You can put your hand up and you'll feel the sun's energy heating it up. And that's because the infrared or thermal energy warms up the molecules in your hand. And so your hand is a thermal detector. So you don't need your eyes. What superconductors do is they change their resistance based on the amount of heat that's hitting them. They can go from a couple of ohms, what's called ohms of resistance, to zero resistance. And they could do so in a very, very tiny amount of heat. And so they become an exquisitely sensitive thermometer, which when attached to a telescope and then incorporated with it polarizing filters, becomes what's called a polarimeter. So we built this polarimeter. We realized we couldn't have it in a beautiful place like San Diego, because what happens to microwaves as they travel in the universe is they can get absorbed by water molecules. That's how your microwave oven works. The water molecules are very highly selectively absorbent to wavelengths of electromagnetic radiation called microwaves. And so we don't want a photon traveling for 13.8 billion years to get absorbed in a water molecule in the atmosphere. That would be very tragic. And even though San Diego is pretty dry, especially right now, there's still tremendous amount of water vapor in our atmosphere. Mm-hmm. So we realized, my colleagues and I, we could take it to a very dry place, and that is the South Pole, Antarctica. The best place is in space. But as you know, the Webb telescope, which is not even the biggest telescope ever made, costs $10 billion, 10 times the most expensive telescope on Earth, and 100 or 1,000 times more expensive than the projects that I'm working on now, which will be the most. So it was prohibitive to launch it into space. So the South Pole is a dry desert. Most people don't think of it because they see the ice and they think it's, they see some penguins splashing around. But the South Pole itself is completely desolate, completely flat, completely white, 9,000 feet above sea level. So it's very high altitude, and it's extremely cold. So that and Chile in the Atacama Desert, which is at 5,200 meters elevation, 17,000 feet, even higher than the South Pole. Those are the two best places to build these types of radio telescopes. Now, we were looking for a signal. We were looking to see if we could see these waves of gravity. In my case, as I say, Abhijit, I wanted to win a Nobel Prize since I was a graduate student. It was really kind of driving me. I explain in my book that it was partially due to competition with my father, who was a great scientist that I had been separated from because of divorce of my parents. And I wanted to prove him wrong, or show him that I was a great scientist. I didn't need him. It's a little dramatic, but I do describe that kind of origin story. And I think that's the most important thing. My birthday is coming up in just 2 days. And I think we're all fascinated by birthdays. And I was always fascinated by the birth of the universe. And so from when I was a little kid, I realized, well, I could do this. I could beat my dad. I could be a better scientist, win this Nobel Prize. And by the way, I'd understand the origin of the universe, possibly have a great deal to say about philosophy as well as science and maybe spirituality. Who knows? So we built this instrument. We upgraded it like an iPhone. We got new detectors, new megapixel. It wasn't never a megapixel. It's like a millimega. It's only 256 or 512 detectors that we had. So it's not like an iPhone. But it was able to operate at 0.2 Kelvin, so 0.2 degrees above absolute zero, which no iPhone can do, et cetera. So we claimed we saw these waves of gravity making an imprint on the cosmic microwave background. We announced it. We had a press conference. We had a paper, but we didn't publish the paper. We didn't get it peer reviewed before we had the press conference. And this was at Harvard, the very vaunted, famous, most, probably prestigious university in the world. After IIT, which my friends tell me is, they call Harvard the IIT of the West. But anyway, but we had this announcement, and we were celebrated, and it was whispered that someone was going to win a Nobel Prize. I claim by that time I was already not going to win it for reasons I get into, politics and science and sort of competition. We'll leave that leave that non-scientific stuff out. But it was quickly realized just a few months later that we had overlooked something, or we had minimized the impact of something, which is called cosmic dust.
Mm-hmm.
And cosmic dust is not that unfamiliar. If you've ever seen a meteor shower, you've seen cosmic dust. And in fact, for your listeners, I know you've got millions of listeners in the USA. I can't send it. I'll try to send it to you, Abhijit, someday, or I'd rather give it to you in person someday. But for your listeners in the USA, I have a special offer to thank you. And that's if you join my mailing list, which is at briankeating.com/list, I will send a meteorite to the first 100 people who join my mailing list at briankeating.com/list. And this is a piece of space dust, which is really the villain of my book. This is a particle of matter, or a chunk of matter that has been formed 4,500,000,000 years ago, orbited around, eventually crashed into the Earth. It's the product of a supernova explosion. That supernova explosion, as Chandrasekhar and many others taught us, is going to occur and spew out all the materials of the nuclear fusion process that it formed right before it detonates. And that process is going to eventually lead to the formation of planets and the iron in our blood, all sorts of good stuff. But it also makes a smokescreen that prevents us from seeing back to the origin of time if we're not careful. We modeled it. We thought we could understand it, but there was one team, a competitor team, that had the information that we lacked, which was a higher frequency channel of observation, and they were located in space. This is called the Planck satellite. They would not share the data because either they didn't have it at the time or they didn't want to share it with us. We'll never know. But in any case, we tried to do as best we could. We instead made an assumption, a model, that the dust was negligible or we could remove it, neglect it. And we announced we detected inflation. 6 months later, the Planck team worked with us. We published basically a retraction, not of the data. We didn't make a blunder. We didn't leave the lens cap on. We didn't put our thumb in the picture. No, we measured an honest to goodness astronomical signal, not a cosmic signal. And that's what we're trying to confront now with the Simons Observatory. We're trying to, and the BICEP array, it's called, this upgrade to BICEP, it still goes on, still is making phenomenal measurements. We're trying to measure multiple frequencies, multiple polarizations, and map out whether or not the dust signal can be subtracted from the dust plus cosmic signal. So we're basically doing a separate experiment, Abhijit. We're looking just for dust, and then we'll subtract it from the signal that we see, the combined signal. And that's what's so exciting about what my field is doing nowadays.
Right. Now let's move on to a different topic, one that the audience, I suppose, is very interested in, something that is at the forefront of their minds when it comes to space, which is aliens and life in the universe. So what are your views about life in the universe, the origin of life, whether there's life in the solar system, whether there could be intelligent life out there? What do you think about this?
Yeah, it's funny because I was on a podcast with Lex Friedman. He's kind of like the Abhijit Chavda of Texas now. He moved to Texas, and I got a lot of feedback, some good, some negative. But my claim is that that the most honest thing we can say about aliens is that we have no evidence for their existence. And a lot of people say things, as the late great Carl Sagan used to say, space is enormous. We know from recent data how many galaxies there are, hundreds of billions of galaxies, how many stars there are, hundreds of billions of stars in each one of the hundreds of billions of galaxies. We know from the Kepler satellite that there are probably at least 1 or 2 planets around every single one of those 100 billion squared stars. So these are numbers like 10 to the 24th, a 1 with 24 zeros after it. It's astronomical. So therefore, the probability is quite high. I find those arguments almost like wishful thinking. And I do feel like there is a spiritual component to this wish that we would find life on another planet. It would somehow give more meaning to the universe. Most of my colleagues, and I don't criticize them, are atheists. They have no they believe in the non-existence of God, not just that they're agnostic and they don't have a position. and that's fine. I think I can accept that. But I think where they fail to recognize their own shortcomings is when they believe in things that we have no evidence for. Today on my channel, in about 2 or 3 hours, I'm posting an interview with Nick Bostrom. He's the creator of what's called superintelligence, which led to what's called the simulation hypothesis, which in many people's minds, no pun intended, is essentially a guarantee that computing power is increasing exponentially, and it's just a matter of time before we can simulate entire civilizations of the past. And so, therefore, we should have no reason not to think that we are not simulations today. It's a fascinating interview, if I don't say so myself. He's a deep thinker. He thinks about the dangers of artificial intelligence and what it could do if it became super intelligent. I think that's a form of religion too. I think there's a lot of wishful thinking by scientists that there are all sorts of things. Another one is the multiverse. We have no evidence for the existence of another universe beyond our cosmic horizon. We know that's possible, but how many things are possible that are actual? And this is where the alien arguments that I like to make come into existence. So one of the things that I have access to is Antarctica. I've been there twice. And when I go to Antarctica, it's very difficult to get there. In fact, it wasn't discovered until the late 1800s. We didn't even know one of the 7 continents on Earth existed. Then we didn't reach the South Pole until 100 years after that, 1911. And we finally reached the South Pole, and then we never went back again for about 50 years. But be that as it may. Now, if you said to me, well, Brian, there's an awful lot of land on Earth, and by the way, you didn't know about 1/7 of the continental land on Earth, so therefore they're actually underestimated how much life there should be on Earth by a factor of 1/7, 14%, call it. That would be a huge error. And yet there's almost no life. There's no human life on Antarctica. Once you get a couple miles from the coast, you don't even see birds, penguins. It kind of disappointed me when I want to get a penguin. I want to come back with a pet penguin. One of my kids loves them. No, there's almost no life. There's no flora anywhere. And any life that's there, is really from somewhere else. So the point I'm trying to make is just by saying there's so much capacity for life in the universe has nothing to do about the actuality about instantiations of life in the universe. So these people that want to explain, not only, don't forget, the claims are, and I'm involved with some of these projects. I have been involved with my friend Avi Loeb, his project at Harvard called the Galileo Project, building telescopes to look for interstellar objects in our universe, in our solar system, of which he claimed he did discover. And he's on a mission to get not a tiny meteorite like I'll send your listeners in the USA, but a huge meteorite that crashed in from interstellar space into the South Pacific. So he's leading $1 million expedition to collect that. Now, what they're saying is very different. They're not only saying we have evidence for some kind of bacteria in space. No. We have evidence for technology, for intelligence, for extraterrestrials that are visiting the Earth in spacecraft that, in order to get here on a biological timescale, must suspend or modify the laws of physics. So look at all these chains of reasoning that you have to accept. Forget about all the physical reasons that life on Earth is so precious, right? And so rare that there's Earth is basically the only planet, some say, that life could exist on, because it has all these features, one of which, these meteorites, as I keep saying, I'll send to your listeners here in the US on my mailing list. Those meteors, they come in much bigger versions. There's a power law distribution. There's some enormous ones. One hit the Earth 65 million years ago. It was called Chicxulub. That was a bad day for the dinosaurs, right? They should have had a telescope. They should have had an Avi Loeb looking up in space. They didn't. So that wiped them out. Well, if they didn't get wiped out by this meteor, enormous meteor, then maybe we would not be here asking questions as to whether or not we're alone. Oh, and by the way, there could be even more Chicxulubs. There could have been literally thousands more if we didn't have Jupiter in the outer solar system. If it was too close, it would disrupt life on Earth. Is it far away? Look at the moon. The moon is filled with every single crater you see is a direct hit on Earth. Well, the moon happens to be at just the right distance It's the only moon in the solar system that occludes the sun exactly by the same diameter as the sun, apparent angular diameter. And it has these properties that make it a garbage collector. How many planets have those things? How many planets have a moon of that size, exactly the right size, to stabilize the precessional tilt? Things in space would normally just go crazy. No, we have stable seasons, which allow the biological and diurnal processes that are essential to life. So you put together these things. You say, let's say there's 10 different obstacles to creating a StreamYard platform. That to create a YouTube channel. Let's say there's just 10 things. I think there's a almost infinite number. Let's just say there's 10 of them. And each one has a probability of 1 in 1,000. There's a 1 in 1,000 chance that a moon will be just the right size, just the right distance to stabilize the precession. And then another factor is it has a Jupiter-sized planet in the outer solar. Put them all together and say 1 out of 1,000 to the 10th power. So 10 to the minus 3 to the 10th power. So you're talking about just astronomically small numbers that are smaller than the number of planets in the universe, in the observable universe. And I don't think I really care. If somebody told me there's life in Andromeda, I'd say that's great for my great, 2.5 million years from now, we could maybe receive a signal from them because it's 2,500,000 light years away. So all these reasons make me very pessimistic, but I don't say the probability is 0. On the other hand, my colleagues will say the probability of God is 0. And I think that is hard to intellectually rationalize for someone who's an objective scientist.
Yeah, the question of God. What do you think about atheism and agnosticism? I mean, lots of scientists are atheists. Do you think it is necessary for a scientist to be an atheist, or is that something that you don't agree with? Because you said that you are a practicing Jewish person. So what's your perspective on this?
Yeah, I think it's a very interesting question. So if you and I were having this conversation, if StreamYard and YouTube existed, 50 years ago, it would be the exact opposite. You'd be asking me, is it necessary to be religious to be a scientist? The purpose of Harvard University, as I said, the most prestigious, that was founded to teach religion, to teach Hebrew. You couldn't graduate if you didn't know Hebrew, the language of the Jewish people. So it's just interesting to note. Now, I think the best form of science, the best form of government, the best form of society is one that is secular, that has no religious overtones. But I think the best form of kind of moral philosophy, of thinking ethically, and so forth, that belongs, at least religion belongs in the room where the conversation's happening. And to say that there's nothing to say, and that I talked with a very famous scientist on his podcast, Lawrence Krauss, last week, and he and I have talked before. He's been on my podcast. I've talked with people who have great respect for religion. He doesn't. He has almost no respect. But we had a respectful conversation. And the point was, he feels comfortable calling all religions, I'm talking Islam, Christianity, Buddhism, et cetera, Judaism, he calls them fairy tales that we don't need because science has invalidated. I said, okay, let's take that as a given. But Lawrence, do you feel like your book, A Universe from Nothing, which makes the case for atheism? In fact, the foreword is written by Richard Dawkins, and it says this book is like Charles Darwin's Origin of Species. Okay, it's a little bit much, and even I think embarrasses Krauss. But I said, this book purports to have all this to say based on the latest findings in science, which is very untrue. It's very controversial, I should say. That book, do you want it to be relevant in 100 years? And he said, well, I would like it personally, but I said, no. If you look at something like a science book, a good scientist should want his or her work to be irrelevant in 5 years, 10 years. I want my work to be totally irrelevant because I want my students and those that come after me that are smarter than me to stand on my shoulders and my colleagues' shoulders and look farther into the distance. So I think it behooves you to look at a book like the Bhagavad Gita, like the Torah, the Jewish Old Testament, the New Testament, the Quran, whatever. These books have been around for what? How old is the Bhagavad Gita? 20.
I'd say a few thousand years. We're not sure exactly how old it is.
Yeah. So that book will always be relevant, unlike a science book. So I want to had developed both sides of my brain. The brain side that is impertinent and temporary and secular, and then the eternal, philosophical, possibly spiritual side. So for me, they separate. I don't teach my kids the earth is 5,782 years old, as the Jewish tradition holds. I say the earth is billions of years old. I say the universe is more billions of years old. And I say, if you believe in God, do this, study science, because science is the purest translation of the laws of nature, which, if you believe in God, came from God. So therefore, if you want to know God's mind, there's no simpler translational dictionary, thesaurus. There's nothing more simple, ironically, than science. So I think religious people need to study science in order to deepen their faith. And I think that scientists need to be cognizant of the limitations morally and ethically of science, and never equate knowledge, which is what the word science in Latin means, with wisdom, which is what sapien, homo sapien, that's what that means. So I get upset when people say you can get wisdom from science. Nope, you cannot.
Yes, science is all about empirical evidence and observational data. That's all. It's not about wisdom, which is patterns and things like that. Now, talking about religion, there's a related topic, which is consciousness. What are your views on consciousness? Some scientists say that emotions are chemical reactions. Some people believe that consciousness is an emergent property, something that emerges out of complexity, complex systems. Some people say it's something that permeates the universe. What are your views on this?
Consciousness is one of my three big bangs, one of the three things that I am most interested in. And what do I mean by that? Well, we don't understand how matter came into existence from pure energy. We don't understand the origin of space and time, as you and I spoke about at the beginning. We don't understand it. We may never be able to understand it. Furthermore, we don't understand how that inanimate matter, the hydrogen, the helium, and eventually all the other heavier elements on the periodic table, we don't know the fundamental event that caused this inanimate matter to become living, animal. Animal means to move. So we don't understand how that happened. Then we don't understand how this living matter, bacteria, became Bach, became conscious, thinking, capable of intellectual leaps that are timeless. And that's where consciousness comes into place. That's my third big bang. Origin of the universe, origin of matter, origin of life, and then origin of consciousness. So maybe four big bangs then. So in my estimation, it's a great mystery. Now, is it an unsolvable mystery? I don't know. In a sense, our brain has the capability to understand itself and undo things in a way that is not reductionally possible to comprehend. In other words, the reductionists think we're just a bag of atoms. Atoms are made of protons, quarks, neutrons, etc. We can all be reduced to that. So therefore, there's a notion now in philosophy called panpsychism, which is that all different elements of matter participate and can be conscious. I don't believe that. And I think that the existence of free will has to be taken into account when we think about consciousness. And so to the reductionist, they have had to create new ways to explain free will and say that no, free will itself is an illusion. It's a manifestation of something called determinism. And we perceive it because of either quantum stochastic processes or chaotic classical processes. I have an interview with Tim Palmer, who's a winner of the Nobel Prize for climate change, but he also has a new book about chaos and the brain, and it's quite fascinating. I've interviewed many times Sir Roger Penrose. He has ideas that consciousness is a quantum phenomenon that originates in certain cellular structures called microtubules. Those microtubules undergo state reduction, which is what we call quantum wave function collapse. I know you've talked about this. That process is instantiated by gravitational effects, by effects in space-time. So it becomes that space-time itself is now correlated in a very complicated way with the order to collapse a wave function, which then can be perceived in a quantum fashion. Now, his views, along with Stuart Hameroff, I did an interview with both of them a month ago on my channel. They're not widely accepted. Doesn't mean they're wrong, but many people have claimed to not only find holes in it, but refute it via observational evidence. So it's an open question. My attitude is, of course I have free will. I don't have another choice. No, that's a joke. Free will is manifest. And to say that you don't opens up a huge Pandora's box. It allows for the denigration of the human ability to be responsible for his or her choices and to make decisions, life or death decisions about himself and other people. And I've never met someone who I met many people who believe we have no free will, but I've never met someone who acts as if they don't have free will. I think that's very important because nobody, could really function and survive if they felt everything was determined at the moment of the Big Bang. By the way, we don't know if there was a Big Bang, right? I mean, this could be to those that say that determinism or superdeterminism is manifest. I don't think there's any evidence for it. So will a computer ever be able to comprehend, consciousness? Will it ever be able to replicate consciousness as Nick Bostrom, today's video on my channel, represents? I have my grave doubts about it. And to bring this back to where we started with Einstein, Einstein called the following the happiest thought of his life. He said, if you're freely falling, if you're in an elevator and the cable breaks or somebody, you get thrown up in the air, it's before rockets existed, and you start falling back down, you don't feel any gravitational force. It's called the equivalence principle. And you don't have any notion of accelerating whatsoever. You're in pure free fall. And he called that the happiest thought of his life. And I ask a lot of my guests, and I'll ask you, I'll turn the table for a second. Can a computer have a happy thought? Can a computer visualize free fall? I don't know. I don't want to say definitely not, but until it could do both of those things, I don't know how we could have an artificial consciousness. But what do you think?
So I'm not sure about that. Yeah, it's a good question. We don't know if computers can think. We recently have had this news about this this AI in Google. It's called Lambda, I believe, that actually seems to have passed the Turing test. So it does behave like a human being. You can't really tell whether it's a human being talking to you or not, but we're not sure. It's just a sophisticated set of algorithms, most likely. So I don't know if a computer can have emotions, original thoughts, and a vision of the future, a sense of self. So we don't know. It's an open question, and I don't think it's we are there yet thus far.
Yeah, I think we need to do a great deal more investigation into both the quantum, which is the microscopic scale, but possibly into the cosmos. In other words, the largest scales, if there are gravitational effects, if it is true that the brain is not a computer, but even if it is a computer, as Kurt Gödel showed in the 1930s, and Alan Turing showed as well, the so-called halting process or the imitation game. There's a movie called that. And that was whether or not a computer could have a finite set of algorithms to prove everything that's computable. And then Gödel comes along and says, no. Even math itself contains true statements which can never be proven. Therefore, math is incomplete. And we physicists, we are even in worse shape. And because we have no such Gödel theorem, like there's no theorem. A lot of people say falsification. You've probably heard this. If you can't falsify something, then it's not scientific, but that's not really accepted. That's Karl Popper. And, I can say that my astrologer, not my astronomer, my astrologer told me, today's going to be a wonderful day. And then I have a bad day. So I falsified what she said. Therefore, what she said is scientific. No, it's ridiculous. So we have no such luck as physicists. And what is consciousness, if not a biological process? What is biology, if not a chemical process? And here I'm being reductionist. But what is chemistry, if not applied physics? And at some level, the laws of physics have to enter into the discussion. And I think we're we're at a premature state. There's so many open questions in quantum mechanics, so many in cosmology. It's all too hard for me. That's why I stick to something very simple, like experimental quantum cosmology.
Right. Okay, final question for today. What progress do you hope to see in physics, in cosmology, in our understanding of the universe in the next 20 years and within this century?
So I'd be lying if I said I don't, want to see certain things with my instruments called the Simons Observatory in Chile.
Mhm.
I think a good scientist should be dispassionate and not do what I used to do, which is to be hungry to win a Nobel Prize, to become famous, to do the. No, you should say, well, this happened and we make an observation. That's what nature is willing to show us. What I'm interested in is building technology. I think we have too many theorists. Don't tell my friend Jayan Arliker. But really, there's so much theory, and it takes so much effort. There's a famous law. I'll make it clean because I know you have an audience of young people too. Something called Brandolini's law, which is that to refute nonsense takes 10 times more energy than to produce nonsense.
Indeed,
So
yes.
I'm not calling my theorist friends nonsensical or foolish. They're much smarter than me. But it's easier, in a sense, to create new theories than to prove the existing ones wrong. And again, we don't prove people right. We prove everybody else wrong. As I often say, and Isaac Asimov said, if you think the earth is flat, you're wrong. If you think the earth is a perfect sphere, you're also wrong, but you're less wrong than if you think it's flat. And that's what we want to try and do. We want to keep refining and refining, getting rid of the aspects that aren't right. So I see great interest in, outside of my field of cosmology, which I'm hoping to participate and contribute to in the next 5 years, to make maps of the earliest moments of the universe's history, as well as detecting the properties of cosmic neutrinos, of dark energy, dark matter. These are great mysteries that I think we can not prove or disprove. It's very dangerous to do that. I think we can solve things like climate change. I think I'm very optimistic about climate change. I see it as a huge opportunity for developing countries and for developed countries to make scientific progress, and to say the best way to combat it is shut off all carbon right now and just like go back to a more primitive society. I think that's anti-scientific, because the human brain is so adaptable, so pliable, so brilliant, and it's the only example of consciousness that we know for sure exists. I'd be interested if aliens are discovered. I don't expect them to be discovered, but I'm certainly open to it. I'm open to even the investigations that show the possibility for aliens to exist, not just that they actually exist. These are fascinating subjects: life in the cosmos, the origin of the cosmos, and then yes, consciousness. Now, consciousness, I think I have the least to say and I'm most pessimistic about. We can't even agree what the definition of consciousness is from professional consciousness scholars. Nick Bostrom will be on my channel, as I said, in a couple hours. He fails to come up with a concrete definition. David Chalmers, who coined the term the hard problem of consciousness, he also says this. Now, what do they say and what do they believe? Well, they both believe in something called the simulation hypothesis, which we'll talk about in the Matrix some other time. These topics, I think, point to a fact that we are kind of in the leeches and bloodletting stage of consciousness studies, that medicine was in 200 years ago. Phrenology, studying bumps on your head. So those kinds of things are interesting. They don't really turn me on as a scientist because I don't feel like I can do anything substantive. In cosmology, my students, my colleagues, my collaborators, they're brilliant, and we can do a lot, and we'll know more, exponentially more, in just a few years. And that's what's most exciting to me.
Right. If I may add to that, the one thing that excites me the most is gravitation, and that's something we don't understand at all. So I would like to see some progress in our understanding of gravity. The 21st century was supposed to be the century of gravitation. We still haven't made any headway, but let's see. I hope some progress happens.
Absolutely. I agree 100%.
Right. So, Dr. Brian Keating, thank you so much for being on the podcast. It's a great pleasure, and I would hope to have you again on the podcast. For the audience, Dr. Keating's links are in the description below. Go ahead, follow him, buy his books. Thank you, Dr. Keating, and have Have a good day.
Yeah, thank you very much, Abhijit. And don't forget, if you're in the USA, someday I'll bring some to India and around the world. But if you go to my mailing list, briankeating.com/list, you'll get subscribed to my mailing list. I send out cool information about my colleagues and my scientific exploits, as well as win a chance of 100 meteorites that I'll send to you in the mail. So hopefully you'll do that. It's been a great honor to be with you, Abhijit.
Thank you.